iconic 2001: A Space Odyssey. And in the case of astronomy in general, and Alpha Centauri in particular, it's the motion picture films that have really led the way. You know, a lot of scientists, and I think used to and still do, believe that planets couldn't exist in binary star systems, but Star Wars showed us differently, and then eventually Kepler showed us differently. And then fairly recently, the pale red dot experiment confirmed the existence of Proxima b, so very, very exciting. What I'd like to really highlight here is in 2009, James Cameron made Avatar. This is a movie that featured a giant planet, or sort of a Neptune-sized planet called Polyphemus, orbiting in the habitable zone of Alpha Centauri A. It has a number of moons, one of which is not only inhabitable but is inhabited. And you know, this is a very exciting thing. And I think if you just heard the last presentation in particular, there does appear to be, you know, possible evidence of a giant planet there. And of course, at least with our current state of affairs, we can't see if there's a moon. But it's a very exciting effort, and we've got in touch with James Cameron, and he has a few questions he'd like to ask. If we can, I don't know if we can get him on. He's in New Zealand, so if he's not on right away, he will be soon. But it's very interesting to hear from one of the artists himself, and who is really noted for his superb scientific movies. So over to you, James, if you're there.
Can you hear me, Pete?
I can. You're loud and clear.
Okay, great. Well, first of all, thank you for inviting me. I certainly am an outlier to this group, which consists entirely of scientists, and so I won't be able to sling around a lot of the terminology that you guys do, but I can triangulate, I think, from the perspective of narrative fiction, which I do think makes a big contribution to the general popular understanding of the type of work that you do, whether it's the planetary sciences, astronomy, space travel, you know, that sort of thing. It's often their window or their portal, the public, into what you do, and their understanding of it, for better or worse, often comes from the arts. And I have to say, apologizing for my colleagues in Hollywood, it's often for the worse. You know, things tend to be rather inaccurate and paint a very inaccurate picture. I think of the physics of space travel, especially when it comes to interstellar travel, which we have yet to prove as a civilization is even possible. But when I started to write Avatar, we began that project in 2005. It was an interesting time for me because I had been working on undersea projects, deep diving work, for some years at that point. And I was just coming off a project where we had made something like 40 deep dives down to anywhere from 2,000 to 4,000 meters on hydrothermal vents in the mid-Atlantic Ridge, the East Pacific Rise, and also in the Sea of Cortez. There's some very interesting formations in the Guaymas Basin there. And I was doing that for filming purposes, but also to support science. And what I had done with that project, which was kind of unique, and this is going somewhere, so bear with me, is I had encouraged space scientists to come with us on the expedition. Because while certain aspects of, you know, segments of space technology is very well funded, one of the areas that's not very well funded is astrobiology. And so I contacted some of my friends at Jet Propulsion Laboratory. We wound up having a couple of planetary scientists come out with us on our expedition, and their interest was basically in the ice moons of Saturn and Jupiter. Europa at the time was being looked at very seriously as a potential, you know, habitability candidate. And since then, Enceladus has gained a lot of ground, but we weren't thinking so much about Enceladus at the time. This was in 2003. So Kevin Hann, who's one of their top Europa planetary scientists at JPL now to this day, was just a fresh out, PhD at JPL at the time. So they threw him at us. We put him on the ship and took him with us, took him out there in the subs, and we dove at these really interesting hydrothermal vent sites. And we started to put together this picture that there might be, that you don't necessarily have to be in the so-called habitability zone to have habitability. If you've got water, if you've got, chemical nutrient sources, biological energy sources, which could come from things like geological effects like serpentinization that can support methanophilic bacteria and things like that. I'm sure when you get to Penelope Boston's session, she'll talk about all this stuff. So I'm getting a little bit ahead of the curve on that. But the point was that there was a great deal of interest in the Jovian and Saturnian moons, these ice moons. So when I came to write Avatar, I thought, why limit myself kind of parochially to the idea of a planet, a rocky planet, being the only place where life could exist? How about an exomoon? I'm not even sure the term exomoon was in wide use at the time. So I proposed a gas giant, a modest gas giant in somewhere between Neptune and Saturn size, at about 1.2 AU from Alpha Cen A, thinking that it was a slightly brighter star than our sun, so you'd want to be a little farther out than 1 AU. So we were just making this up. It was just a narrative, but I was trying to fit it into a box of plausibility. So we proposed a gas giant, and inspired by Jupiter with its great red spot, this persistent storm, we proposed that there was a much larger storm that gave it an eye-like appearance, and therefore it was named Polyphemus after the Cyclops of the Homeric legends. And so everything sort of made sense within that narrative framework. And we proposed that there was an exomoon called Pandora, or that humans named Pandora, and we proposed an entire ecosystem on that. And the film came out and became, the highest grossing film in history. I don't think because of the planetary science that we put into it, but more because of its, sort of romanticized view of the natural world and the rainforest and our relationship to the rainforest and nature and all those things that people responded to, and obviously the visuals. But for me, it's very important as a science fiction writer to play within the rules of physics and even a certain degree of plausibility. So it occurred to me when I was writing it that I didn't want to do what Star Wars does and what Star Trek does. We all grew up with these in our popular culture, and in Star Trek, Sulu kind of hits the throttle and they go to some other star system in minutes or hours. It's never really said, but at some great warp factor. And while I guess we can't rule all that out, what we know of physics right now says that's not very, very plausible. So I assumed, sub-light speed travel between star systems, and it seemed patently obvious to me that Alpha Centauri, the Alpha Cen system, would be the logical place that we would be able to go first. And you have sun-like stars. I think at the time I started writing it wasn't entirely clear that you could have stable planetary orbits in a binary system, though I think that's been modeled pretty successfully since. You guys know better, and of course that's what you're looking for. So that's tremendously exciting. I just want to say that Kevin Wagner's work and the whole NEAR team is obviously very, very exciting. It's exciting as a methodology, but if their initial result proves out, that's very exciting, because it's right in the sweet spot. You'll just have to call it Polyphemus, please. I beg you. No, I'm kidding. But I don't want to ramble on. I don't want to take up too much time in the Q&A session. But I just want to say that as a storyteller, I think that what you're doing is is really amazing, and I'd love to work with any of the group that's on the session today, or any of the sessions, to help figure out ways to explain to the public what you're doing. That's something that I would happily love to discuss with anyone. We're proceeding with the Avatar film. In fact, I'm in New Zealand right now, working on Avatar 2, 3, and parts of Avatar 4, believe it or not. And the nice thing about New Zealand is I walk out my door at the end of the day and I look up at the sky, and of course I can see the Alpha Centauri system. It's quite bright near the Southern Cross, and so that's always given me a little bit of inspiration over the years that I've been working down here. So just to go back, the writing process was taking place in 2005, 2006, right after my hydrothermal vents expeditions. So I was thinking a lot about exomoons and icy moons. And the thing that's exciting about the potential for a gas giant in the habitable zone is that we don't know of a gas giant in our solar system that doesn't have moons. So we can almost assume that there are going to be moons, and that puts rocky bodies with potential atmospheres in the habitable zone around those primaries. So your candidates for life-supporting environments, I think, are potentially quite huge there. So I've tried to connect the dots between the actual science work that I was supporting. I don't profess to be a scientist, but I do like to support the sciences with my documentary and expedition work. And why I came to thinking of this particular story as involving a moon, an exomoon, around an exoplanet. I'd also like to just say that obviously where this is all going and where what your research tees up to is someday, as a civilization, we're going to try to go there. We're going to try to push out from this star system to other star systems. We're going to have technologies that I think we can barely imagine, that we can probably, we can look at it and say the physics doesn't deny the possibility that we could do, sub-light speed travel. It's an engineering problem. But of course, that engineering problem might take us several centuries or maybe even thousands of years to work out. So I'll be very interested to see some of the later presentations about Starshot and some of the physical limitations of that, and the ideas of beamed energy and so on. I think it's also interesting, we never really, in the film, show how our interstellar mission architecture works. It all exists in a kind of an online, side body of information, which we call Pandorapedia. And there's quite a large section on how they do their interstellar flight. And it's with beamed energy. So what we proposed was a very large phased array of lasers built on the moon in the southern hemisphere near the south pole of the moon on the far side, so it couldn't be weaponized and used against the Earth. And it basically fills a small crater there, and it's used to propel a photon sail that accelerates the starship, and then antimatter annihilation propulsion is used to decelerate into the Alpha Centauri system on the other end of the cruise phase of the mission. And then the process is reversed outbound, where they have a similar system built there. And of course, we sort of fudge how long it took them to build that giant laser array at Alpha Cen to get back. But if you're going to have commerce, if you're going to bring something back from there that drives some kind of interstellar commerce, and of course we're probably centuries away from this at best. So even though I like plausibility in my storytelling, I also fully understand how implausible this is in the kind of near-term horizon of the story. I proposed that my story for 2154, 200-year anniversary of my birth. just picked that date at random, but it ironically turns out to be, I believe, 1 year before the Apoastron in 2155. So the effect of a binary sun would be the least at that point in time, and we never show it. We never show Alpha Centauri B or its lighting effects on the planet, other than there's a pretty bright moonlight on the planet, and of course, I think Alpha Cen B would probably be maybe a couple hundred times brighter than the full moon at that point in its relative position to a planet around Alpha Centauri A. So we tried to get it as right as we can. I would love to get input from anybody on the group that is interested as we go forward in this project, because I think that over time, if the Avatar films are successful, people will start thinking more and more about the Alpha Centauri system. To me, it was just logical that if you were going to ever have any economic driver for going to another star system, it would have to be pretty close. And since they're sun-like stars only 4 plus light years away, that seemed the obvious choice. But of course, you just like Frank Herbert did with Dune, where he proposed spice, the thing that drove the whole sort of galactic economy. I couldn't think of anything that was valuable enough to want to go to another star system and try to mine something and bring it back in any terms that made sense. But there's always been something throughout human history, everything from gold to diamonds to beaver pelts to spices, whatever it was, that got people up out of where they lived, got them on ships and sent them somewhere else to take stuff from other people. That's one thing that the human race has been extremely consistent about. So something will come along that we want and need. And so I just called it unobtainium as a nod to the 1950s engineers that whenever they proposed a part for an airplane or whatever it was they were designing, and it didn't work within their known laws of material science, they just said it has to be made out of unobtainium. So that was just propagating that little kind of engineering in-joke. So we don't know what unobtainium is. It's basically the same thing that was in the briefcase in Pulp Fiction. When you opened it, glowed and lit you up. And who knows what that was. So we don't know what that world might look like, where we have regular space flight to another star system. But all the work that you're doing right now is laying the early groundwork for understanding it. And I was quite struck by the concept that we need to understand the proper motions and the trajectories of these stars to an extremely refined level of detail in order to even send something toward them so that we can have a successful intersection. And of course, Starshot is a remarkable project, and my hat is off to Yuri Milner and to everyone at Starshot for raising the questions. I think we as human beings rise to grand provocations. We think of very interesting problems and then we attack them. And if that provocation doesn't exist, we may not even think about things like this. So my hat is off to everyone who's presented so far today, and I'll be looking forward to the further presentations. I don't want to take up any more of the Q&A session because I'm sure that you have burning questions for each other, but I do have 2 questions myself, and anyone that wants to answer them, I'd love to hear it. I've been a little bit surprised over time following the whole exoplanet story, and we're now up to several thousands of exoplanets that have been found. And of course, I understand why we're finding hot young super Jupiters, and my understanding is that there are 2 methods, now a third, direct observation, but that the main 2 methods have been a kind of Doppler effect causing the star to wobble and a direct occultation of the star. So I'm curious why we're seeing thousands and thousands of exoplanets at orders of magnitude farther away than Alpha Centauri, and we still don't know whether there are large planets around the nearest star system to us. And my question is, why is that? It's not meant as a diss for anybody that's doing this research. It's meant as, you know, what is the factor? So I can explain it in our notes, if nothing else, or in our novel. Is it that the star system is tilted toward us in such a way that the Doppler and occultation effects aren't visible? So that's one question. And the other question I have has to do with interstellar propulsion, which I know is a topic downstream more, but I'm going to fit this question in now before you get to that part of the program, which I think is mostly tomorrow. I won't be able to attend because I'm in production. Which is the thermodynamics of starships bother me. You need very, very, very high energy sources, and people have proposed up to antimatter annihilation, which is I think the highest source of energy that we can imagine under contemporary physics. And yet you're in the vacuum of space and you have to disperse this energy really just through black body radiation. So at what point does your ship just melt before it, you know, what are the upper boundaries of material science for things like photon sails and the actual structure of the ship? And we're talking about these you know, if we can imagine getting there at some fraction of the speed of light, we have to expend a tremendous amount of energy from a physical structure that's moving through the vacuum of space and has a very limited means of being able to get rid of that heat. And I just don't know if there's I'd like to hear, you know, if there's some kind of theoretical boundary just from the basic second law of thermodynamics that says you really can't do that, or you really can't go faster than this speed, or that sort of thing, or material science creates some kind of a boundary. And I don't know if what's been discussed for the Starshot sail material, I'm assuming it's going to be some kind of, you know, carbon lattice, maybe something theoretical, maybe monomolecular diamond or something like that, that doesn't melt when you put that much laser energy onto it. But those are my two questions, and maybe they can percolate around throughout the sessions, or maybe nobody really cares. That's what I've got to contribute for today. And of course, I'm happy to answer a question. I'll stay on for the Q&A if somebody has a question for me, but that would sort of be a waste of everyone's time. But anyway, I do appreciate Pete Worden and Yuri Milner inviting me to participate. And I'm going to sit back and shut up and take a lot of notes as this continues. So thanks very much.
Thank you so much.
Thank you.
That was great. Olivier.
Yeah, so maybe Sarah and I can try to answer your first questions, because I think we're much more familiar with it at the technical and scientific level than the second question. Yeah, maybe drawing on the audience and especially the speakers as well, because they have expertise in answering this question. I think there's a combination of things at play. Why haven't we discovered planets, giant planets yet, if they exist in the Alpha Centauri system? In some ways, our most successful techniques rely on luck, especially alignment, the transit technique, especially, where we can detect planets fairly easily if they happen to transit across the star. But the alignment needs to be within a few % of edge on, and that's not the case for the Alpha Centauri system. So we don't have as one of our tools the technique that's probably the easiest one to find planets, because we don't have the alignment, the luck of the alignment for Alpha Centauri. I think for spectroscopy, which is the second most successful technique, the radial velocity technique, it's been challenging because Alpha Centauri is a binary, and it's hard to disentangle the two spectra. So there's a technical aspect to this that made it more challenging. Sarah, do you want to comment maybe on this, and maybe then we can ask our presenters if they have things to add?
Sure, yes, I'd say we heard before how, well, ironically, we don't have a way to continuously monitor the brightest sun-like stars in space to look for transits. And that includes Alpha Centauri, actually. Believe it or not, I actually had a CubeSat, a small 6-unit CubeSat that's like a prototype to test how we could go to space and send a constellation to monitor the brightest stars, like for as long as we need to search for a transit. So there might not be one, but if there was one, we don't have a way to necessarily find it around Alpha Centauri. So that's one of the challenges there. Does any one of our session members want to chip in? And we had some talks on astrometry. Maybe Rachel can pop in and say, how many more observations do you need to say something more about Alpha Centauri?
Or let me actually just start with adding something to what Olivier said about the radial velocity, and that is that, you know, the brightness of Alpha Centauri and the binarities actually do hinder the radial velocities, but a lot of work has gone in, and as Pierre showed, you know, there are limits to the largest planets. We can say that there aren't, you know, very massive super Jupiters around either A and B based on the radial velocity. And all these techniques that all of us are talking about, we're trying to push down to smaller planets, either finding them or ruling them out. As for the astrometry question, Sarah, you know, what we've done so far, I think is I'd say that's given us a good baseline to get the orbit of A and B really understood. It would take at least, I would say, 20 new epochs at high precision to start to look for deviations and have any sort of confidence if we see something. You know, in general, you want to see at least one orbital period before you would believe anything. So, you know, it's a several-year project on our end for the astrometry.
So one question also I'm wondering myself is, if we look at where major efforts have been deployed from government agencies, it's typically on programs that have a large number of stars being surveyed. There hasn't been it's been hard, I think, to push for efforts that are only looking at one star, however special it is. And this is where, you know, looking at the last few years, I think there's been a shift, much of it pushed by Breakthrough, to focus significant efforts on that one star system because it is so unique. So I don't know what other what Sarah you think about this, and what other presenters think about this, but that I think that has played a major role.
For a second, yes. But first I want to say there was a comment from one of our attendees, Gibor Basri, who pointed out, he wants us to remind everyone that the types of planets we care about, like the small rocky worlds when we're thinking about life, they are very, very hard to find. You know, they might not be transiting because they're so far from the star, and their signals are tiny compared to other things. I do want to second what Olivier said, because it's been wonderful for Breakthrough to sponsor this, and we need everyone else to get around to this as well. Like back in the initial days of exoplanets, we just looked at one star at a time. And now we're so spoiled. Like the Kepler Space Telescope found thousands of planets. We have the NASA mission TESS now is finding so many planets. So to invest so heavily in just one system, you know, there's not that much return for all the scientists to keep working. And so we need to get this paradigm shift that we're starting here to just focus on one object, just a few very special star systems. I think we should try to turn to our to James Cameron's second question. We're trying to see if Harry, our best person to answer this question, is online. He doesn't seem to be, so we'd welcome anyone else of our panelists here to try to take a crack at that one.
Sarah, I don't know if Kevin Parkin is online. He could probably answer the propulsion ones as well.
Sure, I think he's got to get promoted to the panel by our tech folks. There he is, Kevin.
Hello, can you hear me?
Yes.
Okay, so two things. On the thermodynamics, yes, there's enormous amounts of energy involved. The ideal
While we're waiting for Kevin to come back, people are saying that maybe it makes you feel better. The thermal heat rejection, it's not a fundamental physics limitation like some other things that pop up occasionally. You know, it's really just an engineering challenge. Kevin, you're back. Okay.
So the ideal is not to absorb those enormous quantities of energy, except to divert it into propulsion. For beamed energy propulsion, you can look at fiber optics and the history of fiber optic cables. It's an exercise in making materials that absorb almost none of the light that go into it. So on the material science side, it's getting rid of the impurities in materials and getting rid of the voids. I can't speak to the fundamental limits on that, but I can tell you that you can push the limits down far enough that you can propel these sails and absorb almost none of the incident beamed energy. For other schemes like fusion propulsion and so on, yes, you've got thermal radiation, but thermal radiation, if you do have to manage it, it goes with the fourth power of temperature. So once you get to very high temperatures, you're capable of radiating enormous quantities of energy. And there are thrusters that are based on, I think, a nuclear light bulb principle. So instead of radiating from anything that's solid, you're radiating from a plasma, and you're controlling that plasma with fields. So there's a lot that you can do with physics to manage enormous quantities of energy.
Cool. That's great. Thank you. Good. So it's possible.
Yes.
I'd just like to comment that if anybody ever happens to be late at night over a glass of wine watching Avatar, pay close attention to the opening minutes of the film. You'll see a very large starship that's glowing bright red because it's just arrived into the system, and it still hasn't cooled down yet. And there are large radiator arrays that are still glowing cherry red.
Wonderful. Okay, back over to you, Olivier, I think.
All right.
Let's
We've seen.
but before we
sorry.
before we do that, I just wanted to give a huge thank you to James Cameron for dropping in. This was like a huge thrill for all of us here attending. So thank you so much for coming.
Well, it's my pleasure, and it's a huge thrill to even be a tiny part of the conversation. What everyone in these sessions is doing is remarkable and historic.